All right, everyone, welcome back to HDL for Digital System Design. We're going to continue our conversation on combinational building blocks, specifically operators. I'm Dr. Mike Brofchek. It is great to have you all here with me. So let's dive right in. First of all, where does this live? You're going to be writing what looks like code to describe hardware. What does that code represent in terms of the hardware area behind it, right? So every time you use an add, subtract, multiply, shift, it's not just code, right? That code represents real hardware. So experienced designers look at code and see the, the physical area that it takes, where they see the gates that it represents. That takes time, but over time, you'll get better and better at doing this. Where we'll see this specifically. Topic 3, when we looked at the arithmetic logic unit, we're going to use addition, subtraction, anding, ORing, bitwise versus others. So we'll see it. Topic 9, memory addressing using comparators. Topic 11, the UART uses reduction operators for parity bit checking. We will see operators in every single lab after today, and we'll be using this vocabulary. It's important to note that it's not just words. The operators become hardware, and it's not always the same. So you will be asked, if you ever go for an interview that deals with FPGA or ASIC programming of any kind, you're going to be asked to write some area efficient RTL. Right, so if you're going to be designing these types of things in the future, right, ASIC design, FPGA design, this matters. Um, so do you know which operators are cheap versus expensive? This is the step for you to get started to think about that, right? So continue to explore. We're going to scratch the surface here. You're going to take it to the next step. So first off, the mental model that you need to replace. From a programming standpoint, you look at an operation, you're like, oh, A plus B, A and B look the same. They must cost roughly the same. Um, Hopefully you recognize already in programming that's not always true, right? A multiply sometimes is a multi-cycle operation, but regardless, make sure you shift your model. Every operator that we use has a different hardware footprint. So bitwise and 32 bits, 32 LUTs. Addition, 32 bits requires 32 LUTs and 32 carry cells. Multiplication, 32 bits, hundreds of LUTs, um, perhaps even a dedicated block to do this. On our Lattice semiconductor ICE 40, we have about 1300 LUTs. I'm not even sure. Right here, I say the 32-bit multiply can consume 10% of your design. An 8-bit multiply can actually consume 10% of your design. 32-bit multiply, built naively, won't even fit on this design. Um, so let's do a little bit of a refresher. We mentioned LUTs before, lookup tables essentially, but carries we kind of just glossed over. So it's time to maybe spend a little bit more time to recognize that there are two different types of things that we're talking about here. And we're going to count them separately because they are separately programmable. Um, and we have budgets for each of these. We actually have their identical budgets, but they are not necessarily tied together in terms of it's not always a one-to-one usage. So a LUT is a lookup table. 16-bit truth table maps any 4 inputs to a single output. It is configurable, right? It is essentially you have 16 bits of memory, you get to choose the function you implement. It is used for bitwise, logical, mux, reductions, comparators, many different things. Basically, it's the synthesis process. We write what we want and it translates it into, essentially, if it can, a 16-bit truth table 4-to-1 input mapping. Other side, a carry. There are many instances where we need to move information and cascade it to the next um, logical block somehow. Imagine just simple addition. If you are at the max end of your range, right? If you're trying to add two 4-bit numbers together, for example, right? If one of those 4-bit numbers is all ones, and you were to add something to that, what happens? Well, it rolls over, right? You need to carry information somewhere else to the next space that you're going to, right? And so how does that get accomplished? It actually gets accomplished with dedicated hardware that carries extra bits of information, generally directly to its neighbor in a very specific manner. So it's hardwired chain. It is super fast, free in quotes because it's in every single one of these, but it has a very fixed purpose. You get one of these per bit, one cell per bit, chained directly to a neighbor. It is not configurable. It can only propagate these carry values. It's used a lot for addition, subtraction, and then also less than, greater than magnitude comparisons. Why does this matter? In every logic tile we have on an FPGA, we get one LUT, one carry, one flip-flop. You can imagine that LUT generates a sum bit, right? That's great, right? So if I have A plus B, it's going to generate the sum that exists in that 4-input space. And then the carry bit will carry whatever is in excess of that, right? So if you roll over, it will carry the amount of information up the routing fabric. So if you were to do a Yosis stat on an adder, you would get essentially counts for how many LUTs are used as well as how many carries are used. So it's also why if you were to do a Yosis stat on an A and B operation, you would see no carries. There's no carry information required when you're ANDing, logical ANDing between two inputs because there's no excess, right? You can't roll over. But in any operations, again, ANDing, subtracting, addition, subtraction, multiplication, you're going to have information that exceeds the bit width of your input space. So definitely need to take care of that. We do that through the carries. So when we revisit what the logic cell looks like, we have essentially now a logic cell that has 4-input LUT, as we showed in prior videos. We also have this carry that comes along for free that's tied to a handful of the inputs, also takes in input from the chain, the prior cell, and drives output to the next one. So going from the bottom to the top, there's a carry in, as well as going through the top, a carry out. They're all chained together. It also takes in some of the inputs that are passed into the LUT, also get propagated to the carry. Again, this is wired right in, but it's not necessarily burned in or turned on if it's not needed. The rest of the cell is the same in terms of the D flip-flop, as well as our 2-to-1 mux. Basically, it's our 2-to-1 selector that chooses between using the flip-flop or the output of the LUT. So we have a budget for each of these, right? Because it is possible, right, that since the structure of these carries is in a column form from top to bottom of the chain, we could run out of a carry chain before we run out of LUTs, right? So if you were to come up with something that was very complicated in terms of how much information you need to propagate through the carry, but not necessarily in the number of LUTs needed, you could run into some problems. So again, it's important to just note and to recognize that we count those separately towards our budget of how many we've used. Okay, with that information now, let's look at the cost of some of these operands. Up front, the one I'm going to point out first, I'm going to start off about almost at the end of the table. What is absolutely free? Well, what's actually free is shifting. Shifting by a constant amount is nothing more than changing wiring. Basically saying, hey, I want to rewire what bits go where. That's really all a shift is. Okay, let's go back up. Bitwise, logical, and reduction unary operations. Let's start off with bitwise operations. Imagine you have n input or n bit operands, A and B. So they could be 4 bits wide, 8 bits wide, doesn't matter, 16 bits wide. The bitwise operations of and, or, XOR, and basically the negation here between these two essentially operates on a per bit basis. So you essentially need it's not very excessive, right? So you don't have much that you end up needing. Logical ones basically operate on the um, entire whole operand at once. It basically results in a single bit, true or false. And so the bitwise one, your result is the exact same width as your input. The logical one, you basically get a single one. So if you look at the pictures at the bottom, I've tried to represent this. Bitwise, you get the width is the exact same as your starting point. Your logical one always results in a single bit, either true or false ultimately, 1 or 0. The reduction unary starts off with a single input of n bits wide and results in a single bit. You can think of it as a reduction in terms of if you do an and or an or, you're essentially getting whether or not all the bits are 1 or all the bits are, or if any of the bits are on for the or. And the not is essentially, it's not exactly a reduction, but it is going to be nodding every bit. So then arithmetic plus minus. So you need 1 bit, one basically per bit, as well as the carry chain. So you have the cost of not just the operation, but carrying information. Most expensive thing we can have, multiplication. If we need n bits to do addition or subtraction, a very simple approach to multiplication would be repeated addition. You could imagine doing it n times. Doing it that way is incredibly expensive, right? If you were to build out all of this at once, that would be pretty expensive. There are some shortcuts to do it if you want to build out a multiply that's all at once. But you could also consider that instead of doing this, it might be more beneficial instead of doing a multiply directly, if you have the time, to do repeated addition instead. But if you were to build out a full multiplier in hardware, it is essentially the equivalent of building out n additions um, or some factor, not necessarily n, but it gets expensive. Relational operators, so checking equality, less than, greater than, all require essentially, even though it ends in 1 bit, does require a significant amount of hardware. It's going to usually look like a tree of some kind, and you can actually see that in the diagram at the bottom. Building up, we already mentioned that shifting for a constant amount is free. The thing that is not free, that gets people in trouble, is a shift by a variable amount. If you don't know how much to shift by, you need to actually wire up a potential shift of any amount between 0 and the total space that you're in, n bits. And that becomes incredibly expensive in terms of the size requirement. Finally, conditional. Being able to select between A and B comes pretty cheaply in our space. Essentially, depending on the size, right? I mean, we can handle up to 4 inputs in, but depending on the size of our input space, it is going to scale very nicely, incredibly cheap to select between 2 values, A and B. All right, so first up, let's look at bitwise versus logical. In general, I look at this as if I see a single and, that is going to operate on every single bit independently. And that means that the width of my result will be the same as that of the operands. A double and treats each operand as a Boolean, right? And so it will always result in a single bit. It is a pretty classic bug to get these backwards, so practice them, make sure you have them down. Let's take a look to see if we have an example in our space. So let's see if we have a pretty quick check here. So this is in the week 1, day 2 folder, and let's just look to see what we have. We have an operator comparator, which we'll take a look at. Let's look real quick at the width bugs, just to see what's in here, although this might be one that we'll take a look a bit later. So yeah, looks like we'll take a look at that one later. We will look here in a moment at a mux. So let's let's do that. Let's give you a little bit more to look at. So pretty simple here in terms of just, if you have the bitwise and you're going to end up with a result that is of the same size as what you passed in. If you're using the logical and, you're always going to end up with a basically 0, 1, true, false answer. So, okay, where it starts to get interesting here is building out conditional muxes. So 2 to 1 mux, we said was going to be probably pretty cheap, where essentially we say, look, I want to assign, let's say, uh, 0 to A and 1 to B. Could we do it? Sure. What about if I now want to select between 4 different options? Well, one option might be that you are going to build a tree. And so I have it started here. Let's say that I want 0, 0 to go to A, and 0, 1 to go to B, 1, 0 to go to C, and 1, 1 to go to D. Could you come up with the mapping that would do that, right? Where do A, B, C, and D go in this example here? If I want essentially to go in order of numerical count, 0 through 3, all right, 0, 0, 0, 1, 1, 0, 1, 1, to go to A, B, C, and D respectively. I'll let you pause and try to see if you can come up with that mapping. And when you come back, hit play and I'll show you the answer. All right, so welcome back. Here's an answer. If I wanted to set this up so that I got 0, 0 points to A, 0, 1 goes to B, 1, 0 goes to C, and 1, 1 goes to D, the way that I would do this is I'm doing my top level select, right? My root of my select on bit 1, right? Select 1, and I have 2 branches. And in the branch to the left, I'm going to do select 0, where I have D and C. And then on the other branch, right, I'm going to have select 0, and it will be B and A, right? So that is generally how that's going to work. So what is built behind the scenes? Well, 3 muxes in a tree, 2 at the first level and 1 at the root. Let's take a look. That's not the only way you could build these. So if we go and take a look at our directory today, we look at essentially, if we look inside here, we have a example mux 2 to 1 and a 4 to 1. Let's take a look at the 2 to 1 first. So I'm going to just taking a quick peek at it. Day 1, example 2, mux 2 to 1. Let's see what it looks like. You can see how you can build this manually at the top here. Tells us that when select is 1, the output is A. When select is 0, the output is B. So if we take a look, this is taking in, right now it's parameterized. Don't need to know quite yet how that works, but just know that right now it's taking in, it's parameterizing and saying we want to take in a 4 input bit width. So that'll let us essentially parameterize how wide of an input we want to take. And you'll see essentially here the statement that ends up making a difference for us right here. Here's the select. So when select is 1, we are going to choose A. When it's 0, we're going to go to B. Okay, so let's actually just make this. Let's do a make sim, and the top level of this is mux 2 to 1. So let's see what we get here. Okay, so we made it. We have a simulation. It passed all of the checks, but let's take a look at the waveform real quick. All right, so we have here our GTK wave that if you are using the tools that we've provided, you should have access to. TBMux demo is what we just opened. You'll see that there's a handful of signals that we can see, and I can append all of them here. That's a lot of signals. Probably don't need all of these. Why don't we let's just take the U2 here. Okay, so U2 is essentially our basically mux with two inputs. And so what we see is the defined width is 4, and we basically see input here A and B, and a select 0. So when select 0, we get whatever the value is of B. So you basically see that, right? So select is 0, and the output gets selected as B. Let's shrink this down a little bit. Let's zoom and zoom out quite a bit here, because what we want to see here is what happens when select goes to 1. So I'm going to click here at the top. You can see that we're basically seeing what happens when it's 1. We get the output here, output Y of A. Okay. Let's go to a place where A and B have changed, right? So here it looks like we now have A is equal to, basically this is a hex value of F, right? If we want to see this in a different format, if you'd like to see it in binary, we can instead. Let me change that for you just so you can see that it is possible. Right, so there it is in binary, just so that we can see that it matches. All right, so here at, let's just, between 4 and 5 nanoseconds, we have A is equal to 1111, and B is all zeros, and the select is 0, which means we're going to select the B branch. And we go a little bit further here, it's 6 to 7 nanoseconds. We didn't change our inputs, but we changed our select, and we now get the value of A. You can do this pattern, look at it all the way through, and notice that the comparison, basically our mux works as expected for the values that we've provided here. Okay, so let's go back for a second here, and let us take a look at something else. We looked at the 2-to-1 mux, but let's take a look at the 4-to-1 mux. We mentioned earlier that there were potentially different ways of building out our mux. And so if we look, the way that we built it out in our demo was essentially a nested chain, right? Using essentially two constructs of the basically the mux here, where we basically have assigning top level, right, the root, and then essentially two nested ones here on selecting on 0. So essentially exactly mapping what we had before. Not the only way to do it though, right? You could say, well, what about if if I have 4 options? Could I have done something like, if you're familiar with in the programming space, a case statement? I basically say, hey, look, I have 4 options. Why don't I just, for 0, 0, I want it to be A. For 0, 1, I want it to be B. For 1, 0, I want it to be C. And here the default, but 1, 1 would be D. So 2 different ways of doing it. The question is, does this yield the same type of result? They work the same. If I were to, let's do a make stat, and let's do top equals, I think mux 4 to 1. And let's do the nested version first. Let's see what that results in. Well, it results in 12 LUTs. Okay. Will that be the same if we do the case version? The answer is no. It is slightly different. Now, depending on the level of sophistication of your synthesis tools, they could synthesize to the same thing. But in this particular instance, these two happen to generate slightly different hardware and yield a different result in terms of what hardware is required. Okay, so given that, let's now take a look at another question here. We looked at the fact that we developed a MUX. Basically, um, the big difference between this example right on the screen and what we just saw is this assumes single, well, we don't actually know the size of A and B in these. And in the example we just saw, we specified them as 4-bit wide each. That's the only real difference. So now your turn. What do you think the costs are for these various operators? So take a moment, might need to rewind a little to look at our table, but guess or take an idea of what these might cost. Um, Pause and come back when you think you have at least a ranking of low, medium, and high. Okay, welcome back. Here's what I would predict here. 4 should be free, right? We mentioned that anything that is a fixed shift is nothing more than a rewiring, doesn't cost us really any hardware. Number 1, the AND here, essentially 8 LUTs, roughly. 6, the essentially a comparison, it's going to take 4 LUTs. 2, the addition, it's going to take some LUTs and some carries. By the way, if you don't know exactly how many LUTs things are taking, I mean, again, things are roughly taking 1 bit per, or 1 LUT per bit width. But again, if you don't quite know, that's okay. But as long as you recognize that there's LUTs and carries, that's going to be good, right? The multiply here, we're going to actually see that here in a second. We assume it's going to take more LUTs, right? And 3, the 3, the multiply, and 5, the barrel, essentially the unknown shift width. So 5 and 3. So that is our shift by an unknown size. The multiply are definitely our most expensive, with essentially the multiply being about 140 LUTs. Again, don't need to know the LUT numbers at this point, but if you have that general ranking, right, of essentially 4 being the cheapest, followed by 1 and potentially 6, and then 2 costing some LUTs and carries, followed by 3 and 5 being other expensive ones. That's what we really want you to get. Okay, so let's take a look at this in a live demo. We're going to go back to where we were, and we have a comparison, operator comparison, that you can quickly run pretty fast from the terminal. So again, we open this up. The very top here, there's that op compare. Actually, if you just do, I think, a make stat ops in this particular directory, you're actually going to get, oh, nope, apparently not. Maybe it's just stats. Oops. Let's look at this big file real quick. Oh, it's a hyphen. That would do it. So make stat ops. So it actually will run through and show us the comparison of what it takes to run these. Hype this to more so we can see it real quick. So bitwise and ends up taking 8 LUTs. Adder, 8-bit adder, is 7 carries and 8 LUTs. And a multiply of 8 bits ends up being 142 LUTs and 10 carries. So huge change. So again, just to showcase that what you write in for your Verilog yields very different sized hardware. That's really the takeaway of today. Okay, so same operand, same width, same one line, right, of code for each of these. And essentially what you're getting here is a massive difference. And here's the secret right here. Multiplication blows up, right? So you essentially are getting 18 times the number of LUTs than you need for the adder. And that's really what I want you to take away, is that different operators can consume significantly different area, right? I don't expect you to memorize it. Not, over time you'll get a sense for it, but this should help you. Okay, so moving on. What do we just have here? We had 3 8-bit modules. You run make stat ops, you'll get all of them. You basically see exactly what we've been talking about. The bitwise AND is cheap, the adder costs more, multiplier is the most expensive. Take your time and maybe try a couple of different operations, see what happens, right? Try to characterize these yourselves using the same pattern that's included in the lecture notes. Okay, so like I said, try it yourself. Try changing the bit widths, see what happens. Again, you can, pretty easy also if you wanted to try subtraction or something else, see how it changes. All right, so we have roughly 1300 LUTs. We did a single 8x8 multiplication and that takes up 11% of the chip. Do you think we could even do a 32 by 32 multiplication? I don't think we could do it without some tricks. Okay, so check the machine, right? Rank the LUT costs of add, multiply, shift by an unknown number, equals, all with 16-bit numbers. See what your favorite LLM will tell you. Ask it to do it. Predict, will it get the ordering right? Will it basically get, that your constant shift is free? Is it going to get that, equality is pretty cheap? More moderate cost for addition, barrel shift exponentiation, is that going to be more? And is the multiply the most? Will it get it right? I will say the AI probably is going to get this right, but the number, the LUT counts are probably going to be off. So you could even give it the exact example we just ran and see if it gets the right or even close to the right LUT values. My suspicion is it's going to way underestimate the LUTs required for a multiply. All right, so the ranking should be right with an AI, but verify any actual numbers using Yosa's stat, okay? All right, Yosa's stat, like I said, is our ground truth. AI can be used if you want rough sizing, but would not rely on it. So, big takeaways. Bitwise AND, per bit, logical AND, 1-bit true-false response. Basically, this ternary operator, the question mark colon, is a mux. You can nest it for wider muxes if you want. Constant shifts are free, but variable shifts are incredibly expensive, right? It's almost never worth it. All right, multiply costs, about n squared LUTs based off of the size of your input. You always should check utilization, all right? Okay, every operator ultimately has a price tag, right? Look, your receipt is essentially the stats, okay? So next up, we're going to talk about size literals and width matching. So we just saw that essentially when we do 8 plus 8, we get 8 LUTs, 7 carries. But what is the bit width result if you were to do 8 plus 8? Is it 8 or is it 9 bits? So here's the question. If I define something, right, 15 plus 1, and they're both 4 bits wide, the answer is 0, not 16. We have to size our result correctly. Video 3 is going to tell us why and how to do this, because the bugs are pretty much silent. Okay, thank you all. See you next time.